So let's begin with section 2, an introduction to statistics. Before we begin, I would like to put forward a small disclaimer. So statistics is a really vast topic, and covering each and every concept from this subject is beyond the scope of this course. So what we would do is, we would cover a couple of few important topics that will be required while we go ahead in the next module of machine learning. We learn those important topics with a bit of abstraction. Like, I presume most of the users who would be watching this video tutorial would not be having a math background. So I'll abstract the math and I'll just put forward statistical concepts with layman terminologies so that you can understand them as simple concepts. Definitely you would need to do a little more reading in case if you have basic understanding, like if in case you miss out some understanding of math. I would highly recommend you to read up some material before we move on to the next module, machine learning. So let's get started. We will cover a couple of very simple terminologies that you've probably come across already. Here are a few basic terms, and I'm sure most of this is something which we have already learned. We have three different sections over here: measures of central tendency, measures of variability, and the normal distribution. And most of this has somehow been already discussed to a certain extent in the previous slides. So let's start with measures of central tendency. We have three simple terms or three simple measures that fall into this bucket. That is the mean, median, and mode. We already know these concepts. Mean is basically the average of the entire sample or distribution. Median is the 50th percentile or the middle value in the entire sample. Mode is that value which occurs most frequently in the data set. So let's say, I think we've not covered mode previously. So let's say, to give you an example, consider 100 students, they have given a test and we have 100 scores. Now if I tell you mode, let's say around out of 100 students, around 35 students, or let's say around 25 students have scored 65. And 65 is the most frequent number in the data set. That would be the mode. So mode is basically the most frequent number that occurs in the sample or the data set. Now, just using these three, mean, median, and mode, can kind of get a fair understanding visually of the central tendency of the plot. And to understand the variability, that is dispersion, we have range, variance, and standard deviation. Range is basically, as you already know, maximum minus minimum. So we understand where does this plot start and where does the plot end. Variance and standard deviation, as we already know, are simple measures of data dispersion. How spread is your data? So standard deviation is a follower from variance. Standard deviation is a square root of variance. And standard deviation and variance is basically the most popular statistical measure used to study data dispersion. Moving on, we have the normal distribution. Normal distribution is one of the most important distributions in statistics. It has different properties that make it really unique and extremely useful for further analysis. So what are the properties of a normal distribution? Now, you would have probably already heard it, and we've given a small demonstration in the previous slides. It's called normal distribution, and it looks like a bell curve because it kind of resembles a bell shape. Now, what are the properties? It's symmetric around the mean, it's unimodal, and it's asymptotic. Which, when I say it's symmetric around the mean, so the mean would be at the center. Let's say this is the mean. And if I cut this into two halves, the first half and the second half would look exactly the same. That's why it's symmetric. It's unimodal, which means that there's only one value which occurs very frequently, and that most frequently, and that comes in the middle section. So if you observe over here, we have the values 140, 160, right? And if you look at the middle bucket over here, this one, this is that value which occurs most frequently in the data set. And if you just, so probably we have used a bucket of 10, like bin size is 10. But if you use a bin size of 1, let's say you just plot the frequency of one single value, you'll still see that the frequency is so high that it comes as in the middle as a center point, and it lines up as a single partition which divides both of them in two halves. So in the normal distribution, we have the property that we have the mean, median, and mode as the same. So let's say for this, 150 would be the mean, 150 would also be the mode, and the middle value will also be 150. That's one property of the normal distribution. And another point, it's also asymptotic, which when I say asymptotic, if you, now this is a histogram, but then when you, let's say, plot a simple plot, you can actually see that the lines over here never really touch the axis. It kind of, it runs as a never-ending, like it doesn't really touch the axis. It just keeps running as parallel lines towards the end, and it is completely determined by the mean and the standard deviation. Now, why is the normal distribution so important? It's because of the characteristics of the normal distribution that we can actually rely on the ground truth and use a lot of probability statistics. Now, this is where we have descriptive statistics and inferential statistics. So what happens is, let's say you're trying to do a simple analysis. You're trying to see what is the average height of men in a country like India. So let's say you have a population of 1 billion, around, let's say, 50% will be men, and you don't really have the luxury to go and measure the height of all 50 billion people, right? So what do you do is you'll actually calculate, you take a simple sample, which is, let's say, around like 1,000 men or 10,000 men based on some analysis. You'll stick on to this 1,000 member sample or 10,000 member sample, and you would get the numbers which will actually have some mean, median, mode, and the variabilities over there. Now, since we have a normal distribution with some specific properties, we can do inferential analysis, which means that, see, basically, let's say if you have a sample of 10,000 members, and it might be a true representative of the overall sample or overall population, what makes you 100% sure that the sample's mean is actually the population's mean? So how can you be so confident in saying that, okay, you just measured height of 10,000 people in India, and you've got a number saying that the average height of men in India is around 5.7, 5 feet 7 inches. How can you say confidently that the average height of all the men in India are actually 5.7? So we have two terms over here. We have the sample and the population. Sample would be the 10,000 member group, and the population would be all the men in the country, which is India. So that is where we have the normal distribution in the picture. In simple terms, the normal distribution, because of its properties, allows us to make inferences about the population from just the sample. I'll not get in the depth of it. We move on to a very important term, the central limit theorem, which will help us understand this better. So, central limit theorem is a statistical theory that states that given a sufficiently large sample size from a population with a finite level of variance, the mean of all samples from the same population will approximately be equal to the mean of the population. If we break this down to a more layman explanation, we can say the mean of the sample is more or less equal to the mean of the population, which means that when you have a sample, and if you calculate the mean of the sample, and the sample size is sufficiently large, and all the criteria mentioned over here are actually met, you can actually infer that this mean, which is of the sample, is actually very close to the mean of the population. That's how you make inferential statistics based from a sample. Instead of going ahead and calculating the mean for the entire population, which is not the possibility, you have a sample and you go ahead and calculate the mean of the sample, which helps you understand that this is really close to the mean of the population. And also, samples will follow an approximate normal distribution pattern, with the variances being approximately equal to the variance of the population divided by the each sample size. Similarly, we have another important topic, z-scores and standard error. Now, what is z-scores? Z-score is nothing but a standard score. Now, to put it in simple terms, let's say if I give you basic numbers, let's say something like out of 100 students, on an average, let's say one student has scored around 75. The score obtained by one student in the test is around 75. And let's say when I give you the mean also, the mean is around, let's say, 65. You will have a fair amount of idea that basically this person is somewhere above the mean and then below the maximum level. But then you still don't have concrete idea about how does this student fare with all other students. Like where does he stand in the entire class? What is the percentile that he's obtained? Now, if you look over here, you won't really have an idea where does the score come? Does it come over here? Does it come over here? You will just have an approximate idea. Or in some cases, let's say if I just don't give you the mean, I'll give you just a number. It becomes extremely difficult to understand how does the student perform in comparison with all his peers for the test. Now, z-scores is a standardized score which will help you to exactly understand how does one student, with the help of z-score, how does one student perform in comparison with all other students. Now, let's say it's as simple as, let's say if I give you a z-score, you will say, okay, fine. With that score, I can say that the person has somehow reached this point, which means that he's approximately 80th percentile in the classroom. So let's get into depth. Z-score has the formula. I'll say z-score is equal to the raw score minus the mean upon standard deviation. Now, if you try to interpret this value, I'll say z is equal to raw score minus the mean upon standard deviation. Now, this actually helps us understand how many standard deviations is the score above the mean and below the mean. So if the z-score for a student is around, let's say 1.5. Now this would be interpreted as this person has scored around 1.5 standard deviations above the mean, and you can fairly get an idea. Okay, let's say if this is normal distribution and this is the mean, and 1.5 somewhere here, you'll get a fair amount of idea that this is where a student has performed with respect to the entire classroom. So z-scores help us interpret the percentile values for each value in a sample in a very easy and layman way. So here we can see a basic z-score sample. Over here it's -2, this is 1, 2, and 3. So a person who has scored somewhere over here would be 3 standard deviations away towards the right from the mean. Similarly, he would have scored less also. Let's say he has a standard deviation z-score of -2. So his score is basically 2 standard deviations below the mean. So we can have a score of plus and minus, and this will go up to standard deviations. But then the moment you cover up to 3, we have approximately 99.9% of the entire sample covered. So that's z-score. Similarly, we have another important metric, a statistical measure called standard error. Standard error is defined as the standard deviation of the sampling of a statistic. I know this might sound a little confusing. Let me give an example. So let's say the example over here is sampling distribution of the mean. Now what happens over here is, let's say you have a sample of 100 members, and or let's say you have a population of, let's say, around, you have a large population of around 10,000 samples, 10,000 records, or 10,000 training samples. Now, what you do is you actually take a smaller sample, or let's say of 100 rows, and you take and you take a mean of that, and you repeat this process several times. Now you have, let's say, 1,000 rows. Out of 1,000 rows, every time you take 100 rows, take a mean. Again, you take a sample of 100 rows, take the mean of that, and you make a note of it. If you repeat this process around 10,000 times, you will have 10,000 values of mean of that entire population, right? Of the sample. Now, for these 10,000 observations that you have noted down while taking your sample and the mean, if you plot that, that would actually be the sampling distribution of the mean. I'll just paraphrase this. So let's say you have around 1,000 records, and out of these 1,000 records, you take around 100 records to form a sample, and you calculate the mean. Let's say the first time you do this, the mean was around 6.5. Then you again take a random sample, and you again take the mean. Now let's say the sample's mean was around 6.9. And you repeat this process. Every time you note the sample's mean, and you repeat the process again. And you repeat this around 10,000 times. So at the end of this exercise, you'll have 10,000 different values of mean. It should be, let's say, 6.5, 7.5, sometimes even higher, 8, or something like that. Now, if you do a distribution of these records that you have calculated, that these 100 values will be 1,000 exercises give you 1,000 values of mean. And if you do a plot of these 1,000 values, that will actually be the sampling distribution of the mean. Now, had this exercise been done with some other statistic, let's say instead of mean, you would have taken the mode or the median or something else, or let's say something like minimum, maximum. You would normally use mean as the most common thing. You'll also use in some cases some other statistical measure, but then most probably you stick around with mean. Now, that's why sampling distribution of the mean, because it's actually several samples taken to calculate the mean, and then you have a distribution of the mean of those samples. Now, what is standard error? Standard error is the standard deviation of the sample. So, if you go and paraphrase, you have 1,000 records, you take a sample of, let's say, 100 records, you calculate the mean, you repeat this process around 100 to 1,000 times. So you have 1,000 new record, 1,000 values of a mean, and you do a plot of that. That's the sampling distribution of mean, and then you take a simple uh, standard deviation of that distribution. That is the sampling distribution of standard deviation of the sampling of a statistic. So of a statistic over here is the mean. That's why the standard deviation of the sampling of mean. I know this might sound very confusing or it's a very long statement to understand, but then at the end, this is a simple way to understand how much standard deviation does your sampling distribution have. And that helps us understand the stability of a particular parameter or a value. We'll be using the z-score standard error together a lot while we do statistical modeling like linear regression, logistic regression. You can actually understand, let's say if I give you uh, the beta value is basically a coefficient of a variable, and I'm saying the standard error of this beta variable is a value. Now with that value, and if you take up the mean, you can actually understand how stable these values are. If there's a higher standard error, you can fairly understand that there is a lot of variations in the samples. You won't really have a lot of stable values. You can't really trust these values. So this is basically useful to understand how stable or how stable your actual value would be. That's standard error. We now move on to probability distributions.